What's up, algebra bros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to talk about orthogonal sets, and we're going to have an introduction to orthogonal projections. And let's go ahead and we'll start with some examples determining whether or not a set of vectors is an orthogonal set. And we ended with this in the last section. We'll go ahead and we'll start with it right now. Remember, for two vectors to be orthogonal, so we'll say given vectors u and v, they are orthogonal if their dot product u dot v gives us 0. And we remember the dot product from last time, so let's go ahead and take a look at these. Just to make it a bit easier with my set of vectors, let me give them little nicknames. I'm going to nickname them A, B, and C. And I just want to go through pairwise, so two at a time, and find their dot products. So let's start with A dot B. So if I do the dot product of A and B, remember we multiply corresponding components, we sum the products. So we're going to get -1 times 5 gives me -5, plus 4 times 2 gives me 8, plus -3 times 1 gives me -3. And if I go through the arithmetic, -5 and -3 is -8, plus 8 gives me 0. Not so bad. And then I can take a look at B and C together. So we can do B dot C. And then here, first components, 5 times 3 gives me 15. 2 times -4 gives me -8. And 1 times -7 gives me -7. And we'll say, oh, okay, so then here I have 15, and then -8 minus 7 gives me -15. 15 and -15 give me 0. So it's looking pretty good, right? And we saw A and B were orthogonal, and B and C were orthogonal. So then, shouldn't that mean that A and C are orthogonal, right? This nice transitive property? No. No. We don't have any transitive property like that. I gotta check it. So, introduce the hashtag, check it before you wreck it. I need to check A and C together. I did A and B together. I did B and C together, but A and C, I got to find their respective dot product. So looking all the way on either end, -1 times 3 gives me -3. 4 times -4 gives me -16. And then -3 times -7 gives me a positive 21. Let's see what we're going to get. -3 and -16 is -19, plus 21 is going to give me positive 2. And this is an issue, right? Because 2 is not 0. So we'd say the set is almost, but it's not. The set is not orthogonal. So this is not an orthogonal set of vectors, unfortunately. Unfortunately. Well, as with any carnival game, we try our luck again. Let me give these vectors some nicknames. Let's call it U, V, and W. Let's do U and V. So the dot product, U dot V. So let's see here. So I have 2 times -6 is going to give me -12. Plus -7 times -3 is going to give me positive 21. Plus -1 times 9 is going to give me -9. And then if I go through the work here, -12 and -9 is going to give me -21. Plus 21 is going to give me 0. So far, so good. And I learned my lesson last time. So let me check U and W. So on either ends, we'll do U dot W next. So I have 2 times 3 is going to give me 6. -7 times 1 is going to give me -7. -1 times -1 gives me positive 1. We'll combine all these together. So 6 and 1 is 7. 7 minus 7 gives me 0. looking pretty good. So I did the first vector and the second vector, then I did the first vector and the third vector, but what I'm left still I have to do the second vector and the third vector, so I need v dot w. Remember, the order that we do the dot product doesn't matter, so v dot w is the same as w dot v. And let's find those sums of products, right? -6 times 3 is going to give me -18, plus -3 times 1 gives me -3, plus -1 times 9 gives me -9. Now I can see looking at this that it's not going to work out very well. We can go ahead and think about what this is going to give us. If I split up the -3, I can take a -2 to join with a -18 and a -1 to join with a -9. So we have -20 and -10 gives me -30. Should get -30 from that. And hey, although it has a 0 in it, it is not the number 0. -30 is not 0. So the set is not an orthogonal set. Depending on your personal feelings, we might put a frowny face because we maybe want the set to be orthogonal. That's what we're here to talk about today, anyways. Hey, let's try one more time. Third time's the charm. Maybe this one's not going to work though. Let me give them classic nicknames ABC. Let's find those dot products. Now we have vectors in R4, worth mentioning. The vectors have 4 entries, so that's just more fun for us. So A and B dotted together. 3 times -1 is -3. -2 times 3 gives me -6. 1 times -3 gives me -3. And 3 times 4 is going to give me 12. And if I go ahead and combine these, -3 and -3 is -6. -6 and -6 is -12. Plus 12 gives me 0. So that looks good so far. And then we'll do A dotted with C. So the first and the third vector. 3 times 3 gives me 9. -2 times 8 gives me -16. 1 times 7 gives me +7. And 3 times 0 gives me 0. And we'll say, okay, 9 plus 7. And forget about the 0, right? I'm adding it. Doesn't do anything. Nothing impressive. 9 plus 7 gives me 16. And then -16 gives me 0. And now I have to check B dotted with C. So -1 times 3 gives me -3. 3 times 8 gives me +24. -3 times 7 gives me -21. And then 4 times 0 gives me 0. If we take a look at what this is going to give us, -3 and -21 gives me -24. Plus 24 is going to give me 0. So all of my pairwise dot products are 0. So we'll say yes, this is an orthogonal set of vectors. We're happy about that. We did it. You did it. You did it. Proud of you. Very pleased with how that turned out. Doesn't get any better than that. All right, well, why do we care about an orthogonal set of vectors, right? Why are we doing these exercises? What's the situation? Well, if I have a set, capital S, of vectors, u sub 1, u sub 2, so on and so forth to u sub p, and if this is an orthogonal set of non-zero vectors in vector space Rn, then the set S is a linearly independent set, and since it is a linearly independent set, that means it is a basis for the subspace spanned by S. And let's see if we can show that this is in fact going to give us linear independence. So if I have this set of vectors, u sub 1 through u sub p, we'll say, okay, consider then the linear combination made up of these vectors. So we'll say, let's have coefficients in here. We'll do c sub, already got a funny stray mark. I'm gonna erase it because you're worth it. You're worth more. The chalk is getting all over the board. So we'll say c sub 1 times vector u sub 1 plus c sub 2 times vector u sub 2 plus c sub 3 times vector u sub 3 plus so on and so forth plus c sub p times vector u sub p, and then equals the 0 vector. Now we want to show that the only way that this is possible is that if all of the coefficients are in fact 0. I want to show that this is linear independence. So what are we going to do? Well, there's actually a nice trick that we can employ here. So I'm going to take my linear combination. Let me rewrite it. So we're considering this linear combination, and then equals the 0 vector. And what I'm going to do is I'm going to take both sides and I'm going to dot it with vector u sub 1, for example, without a loss of generality. Dot it with vector u sub 1. Now, over here on the left, I have a lot of stuff I can work through, but what I want to do is I want to use my properties from last lecture to bring in this dot product and bring the coefficients in front. So I could say c sub 1 times, we have u sub 1 dotted with u sub 1, plus c sub 2 times, we have u sub 1 dotted with u sub 2, plus c sub 3 times, u sub 1 dotted with u sub 3, plus so on and so forth, plus c sub p times u sub 1 dotted with u sub p equals, and then here on the right-hand side, when I have a vector and I dot it with the 0 vector, all of those products are going to be 0, and then summing all the zeros is going to give me the 0 constant. Remember, dot products give us scalars, so that gives me 0, the number 0. And there's something else I can say. So we said that these vectors, a couple things about them. We said they're non-zero vectors, and that they're orthogonal vectors, that I have an orthogonal set. If these vectors are orthogonal, that means, let me get a different color chalk here. I love the baby blue. Let me know in the comment section below if you love the baby blue as well. Or if you don't, let me know what your favorite color is. And of the choices, or just in general, if you have other colors you like. But here, since these are orthogonal vectors, when I dot u sub 1 and u sub 2 together, it gives me 0. When I dot u sub 1 and u sub 3 together, it gives me 0. So on and so forth. When I dot u sub 1 and u sub p together, it gives me 0. In fact, the only time I'm not going to get 0, since it's an orthogonal set of vectors, is when I'm dotting the same vector against itself. So then in that case, all this is going to leave me with is c sub 1 times u sub 1 dotted with itself, and then all these other terms are plus 0, so on and so forth, and then equals 0. However, we said that these vectors are non-zero vectors. So in fact, u sub 1 dotted with itself cannot give us the 0 constant. So we'll say since u sub 1 dotted with u sub 1 does not equal 0, this implies then that c sub 1 must be 0. So right away, we have our first result. Now, the idea is, and I'll do one more of these, but I know you're busy people, you got a lot of stuff to do. The idea is that I can do this same process over and over again systematically. So let's show it for one more term, but we're going to, and we don't do it immediately all at once, but we do it sort of methodically, using the same process over and over again. We can then say, well, let's go back to our linear combination. We can show that the next coefficient has to be 0. So it's going to be c sub 1 times vector u sub 1, c sub 2 times vector u sub 2, c sub 3 times vector u sub 3, plus so on and so forth, plus c sub p times vector u sub p equals the 0 vector. And then what I want to do is I want to dot against vector u sub 2. We can just go all the way down the list, right? So it's a bit of a labor of love, but we can do this. And here on the left-hand side, I want to bring that dot product in. So c sub 1 times vector u sub 2 dotted with u sub 1, plus c sub 2 times u sub 2 dotted with u sub 2, plus c sub 3 times u sub 2 dotted with u sub 3, plus so on and so forth, plus c sub p times u sub 2 dotted with u sub p, and then equals, here on the right-hand side, u sub 2 dotted with the 0 vector is going to give me the 0 scalar. And we can make some comments here, right? We would say, whenever we're dotting two different vectors from an orthogonal set, it should give us 0. So for example, u sub 2 dotted with u sub 1 gives me 0. u sub 2 dotted with u sub 3 gives me the constant 0. U sub 2 dotted with u sub p gives me the constant 0. And then everything in here, these would be different vectors that I'm dotting, even though I haven't shown the specifics, would give me 0. So in fact, I'm only left with where I'm dotting the same vector against itself. So that would be c sub 2 times u sub 2 dotted with itself equals the 0 scalar. But we know that u sub 2 is not allowed to be the 0 vector, right? We said a couple things about it, that it is an orthogonal set of non-zero vectors. So the vectors are non-zero vectors, non-trivial vectors. So this means since u sub 2 dotted with itself cannot be equal to 0, then it follows that c sub 2 must be 0. And then we'll say, repeat, so on and so forth. We can show them that all of these constants have to be 0. So c sub 2 has to be 0. We showed c sub 1 has to be 0. We could show c sub 3 must be 0, so on and so forth. C sub p must be 0. So all of these are zeros. So this is actually important. Before I sort of jump ahead to what's next for us, if I have an orthogonal set of vectors, if I can show that my set is orthogonal, then it is going to be a basis for a subspace. Because I can already tell you, if these vectors are orthogonal and they're non-zero vectors, then the set is a linearly independent set. So that's a very important connection for us to make between an orthogonal set of vectors and linear independence. So that's huge. It's a big result. We're going to really need that result for the whole entire chapter that we're going to be talking about here. Let's continue on, though. So the definition, an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. So we have sort of a nomenclature we can use. If I have a basis that is an orthogonal set, we can call it an orthogonal basis for a subspace. And we have a very nice theorem here. It says let u sub 1, u sub 2, so on and so forth to u sub p be an orthogonal basis for a subspace capital W of vector space Rn for each vector y in vector space W, or subspace capital W, the weights in the linear combination y is equal to, and here I have y is a linear combination of all of these orthogonal bases, well, orthogonal basis vectors. Gotta be careful with the way I say it. So y is a linear combination of all of my basis vectors. Those coefficients are given by, in general, c sub j is equal to y dotted with u sub j divided by u sub j dotted with u sub j for j equals 1, 2, so on and so forth to p. So this sort of now talks a bit further about this. It says, since my set is an orthogonal set, that means all of these vectors are linearly independent if they're non-zero vectors. And that means that I have a basis for a subspace. Now with my basis, I should be able to get where I need to go inside of that subspace. So I should be able to take any vector inside of the subspace and write it as a linear combination of those basis vectors for the subspace. But what's really nice is instead of being able to just say, okay, so I can write my vector in the subspace as a linear combination of my basis vectors for the subspace, what's really great about an orthogonal basis is I can tell you exactly how the coefficients, how those scalar weights should look on the linear combination. And that's incredible. That's an incredible result. And we can show this, and it's not dissimilar from what we just did. So we'll say, okay, here I have this linear combination, y. We'll say, let's go ahead and start with this. So we'll say c sub 1 times, I'll write it in the opposite order, c sub 1 times u sub 1 plus c sub 2 times u sub 2 plus so on and so forth plus c sub p times vector u sub p is equal to y. And what I want to do is I want to show that I can build out these coefficients to my linear combination without having to actually solve for them using, matrices and things like that. We can actually just use dot products. So what I'm going to do is I'm going to dot both sides with, for example, take any of the vectors, but I'm going to start with u sub 1. And we'll just do one example of this. You can sort of imagine how the rest is going to look. So if I dot with u sub 1, over here on the left, I want to bring that dot product through. So it's going to be c sub 1 times u sub 1 dotted with u sub 1 plus c sub 2 times u sub 1 dotted with u sub 2 plus so on and so forth, plus c sub p times u sub 1 dotted with u sub p. And over on the right-hand side, I could leave it written like this. But remember, the order that I do the dot product doesn't matter. So u sub 1 dotted with y is the same as y dotted with u sub 1. I'm just going to write it this way because I think it shows the result perfectly against our theorem. But I mean, it's the same thing anyways. And now what I can say about this, sort of going further, is that whenever I'm dotting two different vectors from my orthogonal set, for example, u sub 1 dotted with u sub 2, that's going to give me 0. U sub 1 dotted with u sub p, that's going to give me 0. All of these pieces inside here that I haven't written the specifics to are going to give me 0. And the only time that's not going to happen is when I dot the vector against itself. So what this leaves me with is that c sub 1 times u sub 1 dotted with u sub 1 is equal to y dotted with u sub 1. And I can actually solve for what c sub 1 is. I can just divide by whatever this dot product is. So c sub 1 is equal to y dotted with u sub 1 divided by u sub 1 dotted with u sub 1. So I've solved for one of these constants in my linear combination. Now I could go through the same process. So if I just, instead, if I dotted with u sub 2 on both sides and went through the same exact identical process, we would be able to show then, that c sub 2 is equal to y dotted with u sub 2 divided by u sub 2 dotted with u sub 2. And I could show this then for all of the coefficients. So we would say in general, because there's a nice pattern here, the coefficient c sub j is given by y dotted with vector u sub j divided by u sub j dotted with u sub j. And that would be for j equals 1, 2, so on and so forth to p, which is the result that we wanted to show. So you can go through and you can systematically show, hey, we can build these coefficients. So this is very, very nice because not only do I know that with my basis vectors, I can travel anywhere inside of my subspace, so any vector in my subspace can be written as a linear combination of the basis vectors of my subspace, but I can also give you that very specific linear combination immediately. And to find it, I don't have to solve for the coefficients. Well, I technically do. I don't have to solve for it in the way that they're kind of unknowns. I can solve for them right away directly with this formula involving dot products. So I do have to solve for them, but I can jump right in and tell you what they are. I can start building them. I don't have to build an augmented system and solve for them with row reduction. Is what's really nice about this. And hey, let's put it to the test. So here we're going to show that u sub 1 and u sub 2 build an orthogonal basis for R2, and then I'm going to express the vector x as a linear combination of the vectors u1 and u2, and I have Spumoni here to help me. What do you think about those orthogonal vectors? I know you're a cat, but what do you think about the orthogonal vectors? She says they're great. Let's, show that u1 and u2, when I dot them together, gives me 0. We have 2 times 6 gives me 12. Negative 3 times 4 gives me negative 12. It's going to give me 0. So here this set is an orthogonal set. And we're saying that we can construct x as some constant c sub 1 times vector u sub 1 plus some constant c sub 2 times vector u sub 2. Since this builds for me an orthogonal basis and a basis for R2, means I can take any vector in R2 and express it as a linear combination of these basis vectors. But what's extremely nice is that I can just build this right away because I can tell you what those coefficients are going to be. C sub 1 is going to be x dotted with u sub 1 divided by u sub 1 dotted with u sub 1. And remember, dot products give us numbers, give us scalars. So I just have a number divided by a number, and then scaled into the vector. And then plus c sub 2. What is c sub 2? Well, we'll tell you that c sub 2 is x dotted with u sub 2 divided by u sub 2 dotted with u sub 2. And now I just have to find, and dot products, right? You probably enjoy finding dot products as much as I do. That's all I got to do. I like finding dot products, so this isn't going to be so bad. I'm going to leave these as vectors u sub 1 and u sub 2 for now, and I'm just going to focus on the dot products. X dotted with u sub 1. So, okay, so 9 times 2 gives me 18, plus negative 7 times negative 3 gives me 21. And then divided by u sub 1 dotted with itself, so think 2 times 2 gives me 4, plus negative 3 times negative 3 gives me 9. Now I'll be back to deal with this arithmetic, but then let me go for the next coefficient, c sub 2. In the numerator, x dotted with u sub 2, I get 9 times 6 is going to give me 54. And then plus negative 7 times 4 is going to give me negative 28. And then divided by u sub 2 dotted with itself, so 6 times 6 gives me 36. Plus 4 times 4 gives me 16. Let's keep going. So let's see if we can build this. So x is equal to, here on the bottom, 9 and 4 gives me 13. On the top, 18 and 21 is going to give me 39. And then times vector u sub 1, plus, here on top, 54 minus 28 is going to give me 26. And then in the bottom, 36 plus 16 is going to give me 52. And then times vector u sub 2. And then I can go ahead and clean this up. So x is equal to 39 divided by 13 gives me 3 times vector u sub 1, plus 26 divided by 52 reduces to 1/2 u sub 2. So this is the linear combination that I wanted to find. So I would present this as the answer. However, what's great about these problems, we can check it right away. So what we're saying is x should be equal to 3 times vector u sub 1 plus 1/2 times vector u sub 2. And we can check this. So it was vector u sub 1, that was 2, negative 3. And then vector u sub 2 was 6, 4. So this is just a check here. Bring it to the bank, we're checking. This is our check. And then x is equal to, okay, so if I bring the 3 in, I'm going to get 6, negative 9, plus half of this vector, I get 3, 2. We add these together. It's going to give me 6 and 3 gives me 9. Negative 9 plus 2 gives me negative 7. Was this x? You better believe it. You better believe it. So I can build this linear combination right away using dot products. Let's take a look at the same exercise, but now we're dealing with, hopefully, a basis for R3. Now, let's just talk about the dot products. If this were an assessment, if this were a homework problem, if this was an exam question, show all of the work for the dot products. Show all the work. Show all the work for the dot products. But since we're just, having a fun time in lecture together, let's just talk it through. U1 and U2, the dot product gives me -1, 0, +1, so that's going to give me 0. U1 and U3, I'm going to get 2, 0, -2. It's going to give me 0. U2 and U3, the last one I'd have to show, I get -2, +4, -2. That's going to give me 0. But you would show all the work, show the work, show that these are orthogonal vectors. Don't skip it. But, right now we're just having a good time in lecture, so we talked it through. Hopefully we can see that these are going to be orthogonal, and hopefully we're comfortable with producing the work to show that. But that means I have 3 linearly independent vectors in R3. This will build a complete basis for vector space R3, which means any other vector in vector space R3 can be expressed as a linear combination of my basis vectors for vector space R3, which means that I can write x as some constant times vector u sub 1 plus some constant times vector u sub 2 plus some constant times vector u sub 3. And I can tell you what those constant coefficients should be. The coefficient on u sub 1 should be x dotted with u sub 1 over u sub 1 dotted with u sub 1. My coefficient on u sub 2 should be x dotted with u sub 2 divided by u sub 2 dotted with u sub 2. And my coefficient on u sub 3 should be x dotted with u sub 3 over u sub 3 dotted with u sub 3. And let's find those dot products. Find them. Gotta find them. The cats love the dot products. Let's start with x dotted with u sub 1. So 8 times 1 gives me 8, plus negative 4 times 0 gives me 0, plus negative 3 times 1 gives me negative 3, and then divided by u sub 1 dotted with itself. So 1 times 1 gives me 1, 0 times 0 gives me 0, and 1 times 1 gives me 1. And then for my next numerator, x dotted with u sub 2, 8 times negative 1 gives me negative 8. Negative 4 times 4 gives me negative 16. Negative 3 times 1 gives me negative 3, divided by u sub 2 dotted with itself. Negative 1 times negative 1 gives me 1. 4 times 4 gives me 16. Got Lily hanging out with us. Say hi, Lily. Help us with the dot products. And then 1 times 1 gives me 1. And then now I want x dotted with u sub 3. So here 8 times 2 gives me 16. Negative 4 times 1 is negative 4. And then negative 3 times negative 2 gives me positive 6. You know, doing dot products, doing math in general is always better with a friend. If you have a cat or a dog, just, you know, make them part of what we're doing. And then I still want divided by u sub 3 dotted with itself. So that's going to be 2 times 2 is going to give me 4. 1 times 1 is going to give me 1. And negative 2 times negative 2 gives me another positive 4. So we got all of our dot products, right? So let's go ahead and work through the arithmetic. So here x is equal to, we have 8 minus 3 gives me 5 over 2 times u sub 1, plus, here on top, I have negative 8, negative 16, and negative 3. So negative 16 minus 3 gives me negative 19. So let's just call that maybe negative 20, but remember I gotta kick back 1. So then negative 28, but it's really negative 27. Sort of some weird Common Core mathematics there. Pretty weird to think about numbers that way, huh? And then 16 plus 1 gives me 18 times vector u sub 2 plus, what do we got here? Well, here we have 16 minus 4 is going to give me 12. 12 plus 6 is going to give me 18. Divided by 4 and 4 is 8, plus 1 is 9, times vector u sub 3. And I can build this linear combination. But let's go ahead and simplify the coefficients. 5 halves times u sub 1. And then minus 27 over 18, I can reduce by 9 on top and bottom. 9 goes into 27 3 times and into 18 twice. And then plus 18 divided by 9 gives me 2 times u sub 3. Thank you for your help. And let's just, you know, I think it's worthwhile to check these. Let's check this one. We'll do 5 halves times vector u sub 1. Minus 3 halves times vector u sub 2, plus 2 times vector u sub 3. And what were these vectors? U sub 1 was 1, 0, 1. U sub 2 was negative 1, 4, 1. All right, negative 1, 4, 1. And then 2, 1, negative 2 for u sub 3. Let's see what we get here. So here for this first vector, when I multiply by 5 halves, I get 5 halves, 0, 5 halves. This next vector, let me bring in the negative as well as the 3/2 so I can think about everything as addition that you can subtract if you prefer. Negative 3/2 times negative 1 gives me 3/2. 4 divided by 2 gives me 2 times negative 3 gives me negative 6. And then here I have negative 3/2 times 1 is negative 3/2. And then plus, let me bring the 2 in. So I'm going to get 4, 2, negative 4. And then I can just work through the rest of the arithmetic. Now 5/2 plus 3/2 is going to give me 8/2. And 8/2 is going to give me 4. 0 plus negative 6 is going to give me negative 6. 5/2 minus 3/2 gives me 2/2. 2 over 2 is going to give me 1. And I still have to add this last vector, the suspense. Let's do it. So 4 plus 4 gives me 8. Negative 6 plus 2 gives me negative 4. And then 1 minus 4 gives me negative 3. So 8, negative 4, negative 3. Yes. Hey, checks out. But this is the linear combination that we wanted to display. So we can write our vector x as a linear combination of our basis vectors. Let's talk about orthogonal projections. So y hat, and this is defined as the projection of vector y onto the line L, which, let me describe that in a bit, is actually equal to y dot u divided by u dot u times vector u. But there's some descriptions that I want to sort of make here. So we'll say y hat is the projection of vector y onto the line capital L through vector u and the 0 vector, or you can think of it sort of like the origin if that helps. And I want to build this orthogonal projection. Okay, well, let's maybe start with a picture. So what do I have is I have some vector u. So this is the vector u. And then here, sort of at the start, is going to be, the 0 vector. And then I have my vector y. And vector y is some other vector. So this is vector y. And what I want to do is I want to find the projection of vector y onto the line L, where line L is through the vector u and the 0 vector. So if I wanted to build this line L, I'll try to do this as best as I can. I'll do it as sort of, well, let's not do it as a dotted line. Let's do it as a solid line. Line L would be through vector u, and sort of on and on and on. This would be the line capital L. And I want the projection. Now for the projection, what we're going to do is we're going to drop this vector y straight down. I'll do a dotted line for this. Onto this line dictated by vectors u and the 0 vector. And this is going to give me some vector, right? So I can go ahead and sort of trace over that. And this is what we call the projection, y hat. We have this symbolism for it. It's the projection of vector y onto line L. That's how we write it symbolically. So this is what I want for y hat. Now, there's this, so that's this purple vector. There's a few things that I can say about this. So let me go over here and sort of write a note. Notice that y hat is a scaled version of vector u. Right? And this vector y could have actually been shorter, and the projection would have been truncated, but it still would be some scaled version of vector u, either smaller or longer, and theoretically it could be exactly the same if it works out that way, but that's maybe not what we're here to talk about. That's a more boring example. But no matter how you slice it, this projection is going to be some scaled version, either longer or shorter, of this vector u. So that means that y hat is some scalar, let me call that number alpha, doesn't matter what you call it, alpha times vector u. So my projection y hat is some scalar times vector u. But there's another very important piece to the puzzle here, and it's this dotted line in purple. Let me sort of talk about it a bit in pink. I use the pink yet. And I want to call this something. I haven't given it a name yet. Let me just give it a name, z. But there's something very important that we can say about this. We can say, well, notice if I take this vector in purple, which is y hat, the projection in purple, and I add it to z, if I think about z sort of as a vector, then we could say, notice that y hat plus vector z, if I think about sort of the adding these vectors together, I'm going to get the resultant is this vector y. So if I add my projection vector y hat and z together, then it's going to give me this vector y. Or, if I sort of resolve this, that z is equal to y minus y hat, just subtracting that over. So I get these very important relationships here. And this is going to actually help me build what I'm trying to show. There's something else that I want to point out. Notice with this vector z, if I think of it as a vector, and my projection y hat, that it is going to form a 90-degree angle. These are going to be perpendicular. So we'll sort of make a comment about that over here to the side. We'll say, notice that z is perpendicular, and then here we can use our favorite word, or orthogonal to, and really, I don't have to say, orthogonal to the projection. It's orthogonal to anything on line L. So we'll say it's perpendicular or orthogonal to anything on line L, which then in particular, let me switch back to my regular chalk. So we'll say in particular, z is orthogonal to vector u. Since my vector u is also on line L, that z and vector u are going to be orthogonal vectors. I can see it visually, but really anything on this line L is going to be orthogonal. So what does that mean? If z is orthogonal to the vector u, that means z dotted with u is going to give me 0. The dot product is going to give me 0. But what did we say about z? Well, right up here we said z is y minus y hat. So y minus y hat, I can make that replacement. Dotted with vector u is going to give me 0. And what did we say about y hat? Well, we said y hat is just a scaled version. Notice that y hat is a scaled version of vector u. So y hat is equal to some constant. I called that constant alpha, but you could call it whatever you want. Some constant alpha times vector u. So I can make that substitution and say, well then okay, y minus alpha times vector u, and then dotted with vector u is going to give me 0. Well, let's go ahead and expand this dot product out. So if I bring in that dot product, then I can say y dotted with vector u minus alpha, some constant, times u dotted with vector u is equal to 0. And I can move that one term over. I can add it to both sides and say, okay, then y dotted with u is equal to alpha times u dotted with u. And if I want to solve for alpha, I would just divide by u dotted with u. So then alpha is equal to y dotted with u divided by u dotted with u. So that solves for constant alpha. But why do I care about that? Well, we said that we want to find this projection, y hat, and that y hat is just a scaled version of the given vector u, but now I know what that scalar looks like. So I can say, okay, then y hat is equal to alpha times vector u, but I know what alpha is, so sort of the result over here, then y hat is equal to alpha times vector u, but alpha, I can see it down here, is y dotted with vector u divided by u dotted with vector u. And this is the result. This is how we can find our projection, y hat, our orthogonal projection given by y hat. So just to recap, got this nice picture too. Y hat is the orthogonal projection of vector y onto line L, and line L is the line that's through the vector u and the 0 vector. And I can build this projection y hat as y dot u over u dot u times vector u. And let's go ahead and take a look at a first example of this. So let me go ahead and get my yellow chalk back, and let me write down the idea that y hat is the projection of vector y onto line L, and this is given by y dotted with u over u dotted with u times vector u. And I want to find the orthogonal projection of this vector onto the line through this vector and the origin. So I have to be able to figure out which is which. And we said that I want to find the projection of vector y onto the line through vector u and the origin, or vector u and the 0 vector, however you want to sort of think about that. Well, that designates which of these pieces each is supposed to be. This is vector y, 1, 7. This is vector u, negative 4, 2. So now I can go ahead and build this projection y hat. So y hat is equal to, it's going to be a scaled version of vector u, but I can find that scalar y dotted with u, and I just have the two vectors, so I have to find their dot product. 1 times negative 4 gives me negative 4, plus 7 times 2 gives me 14, divided by u dotted with u, so u dotted with itself, negative 4 times negative 4 gives me positive 16, plus 2 times 2 gives me 4. And then I can go through the work. So that's equal to, here I have negative 4 and 14 gives me 10. 16 plus 4 gives me 20 times vector u. So we can say, okay, then y hat is equal to, if I reduce, that's 1/2 vector u. And I actually want to find the projection, so I wouldn't stop here. I'll say y hat is 1/2 times vector u. Vector u was that vector with entries negative 4, 2. Right above, remember we sort of labeled these at the very start. So that means my projection y hat is the vector. If I cut this vector in half, I'm going to get negative 2, 1. And that's my projection, my orthogonal projection y hat. And that's how we build it. Hey, that's how we're going to build it. Let's take a look at another example, and this is going to be similar. It's going to involve what we're talking about. But here I have the vector y and the vector u are given right away. I don't have to determine which is which. But it says write y as the sum of two orthogonal vectors, one in the span of u and one orthogonal to u. And the big secret is back up here in our work. It was actually right here. Notice y hat plus z is equal to y. So y is equal to my projection plus vector z. So let me write that down. So y is equal to y hat plus z. And these are two vectors that are going to fit the bill, right? So the sum of two orthogonal vectors, these vectors are perpendicular vectors. One is in the span of u, y hat is in the span of u, and the vector that's orthogonal to u is going to be this vector z. Right? So let's just take a look at the picture to corroborate this. Y hat, my projection vector in purple, is in the span of vector u. It's just some scaled version of vector u, we said. And z is perpendicular to vector u. These are orthogonal then. This is what this is asking for. It wants me to write y as the sum of two orthogonal vectors. One is in the span of u, and one is orthogonal to u. Now, to start, I have to find y hat. So this, I want to remember this, but let's find y hat first. So y hat, it's going to be y dot u over u dot u times vector u. And let's find those dot products. Y dot u goes on top. 2 times 4 gives me 8. 3 times negative 7 is going to give me negative 21, divided by u dotted with itself. So then 4 times 4 is going to give me 16, plus negative 7 times negative 7 is going to give me 49 times vector u. And let's see if I can find the coefficient a bit better. Here on the bottom, so let me sort of pick a 1 away from the 16 and sort of bring it to the 49. So I have 50 and 15 is going to give me 65. And if I do 8 minus 21, that's going to give me, what is that, negative 13. So I get negative 13 over 65 times vector u. And then I can reduce this. That's going to give me negative 1/5 vector u. And let's find this vector. So negative 1/5 times vector u. And what were the entries in vector u? That was 4 and negative 7. So as a vector, let me bring this in. It's going to have entries negative 4/5 and then positive 7/5. And this is my projection vector. So that's one of the pieces that I need. The other piece that I need is z. Now, finding z isn't going to be so bad. In fact, to find z, I just want to compute it as y minus y hat. So just solve this for z. So if y is equal to y hat plus z, then the missing piece z is y minus y hat. So I can take vector y and subtract away my projection vector. And what was vector y? Vector y had entries 2, 3. And then y hat is negative 4/5, 7/5. And I want to subtract these. So I would get a common denominator. You know me. Common denominator, I love them. 2 is really 10/5. 3 is really 15/5. And then I'm subtracting this other vector. Let's see what this gives me. So 10/5 minus a negative is addition. So 10/5 plus 4/5 gives me 14/5. And 15/5 minus 7/5 is going to give me 8/5. And this is my vector z. Now what I can say is I can say that vector y is equal to y hat plus z. And remember, y hat was this vector negative 4/5, 7/5 were the entries. And z, I just found it fresh, 14/5, 8/5. And these two vectors, if I were to just think of them as vectors, if I find their dot product, it's going to give me 0. These are orthogonal vectors. And I have that one of these vectors, namely y hat, is in the span of vector u. And this other vector, z, is orthogonal to vector u. And that if so you could show it, but if you did the dot product of these two vectors, the dot product would give you 0. So I could say here y is equal to y hat plus z, but that y hat dotted with a z should give us 0. And you can check that. You can sort of see it looking here, right? You see one's going to be negative, one's going to be positive. Here I get 7 times 8. Here I get 14 times 4. That's really 7 times 2 times 4 is another 7 times 8. You can actually do the work to show it too. Let's take a look at another example. Here, let y be equal to the vector 3, 1. Let u be the vector 8, 6. I want to compute the distance from vector y to the line through u and the origin. There's going to be some parts to this, but let's start by trying to identify what it is we're looking for sort of visually, geometrically. I want to find the distance from the vector y to the line through u and the origin. You go back to my picture. The picture is really helping out. I want to find the distance from vector y in blue. how far in distance is this from the line L? Well, if I want the distance, that distance would be given here. Think about it by sort of this dotted line. It's this sort of, I kind of have it in purple, but I drew the arrowhead in pink and I've labeled it in pink. So think of it in terms of this vector z. Z is sort of the piece that I'm missing, right? Saying, okay, if I want to go from vector y as a distance, the shortest distance down to line L, it would be traveling along vector z. And to find it as a distance, that means I want the length, the norm, or the magnitude of this vector z. So that's what I want. If I want to compute the distance from y to the line through u in the origin, that means I want, or we want the length or the norm or the magnitude of vector z. Well, what is vector z? Z is given by y minus y hat. So I still have to do all of this work anyways, because I have to start by finding y hat. So y hat is some scaled version of vector u. On top, I want y dotted with u, so that's 3 times 8 gives me 24. Plus 1 times 6 gives me 6. Divided by u dotted with u, so 8 times 8 gives me 64. Plus 6 times 6 gives me 36. So we're just building that projection vector first. I'm going to need it. 24 plus 6 is going to give me 30. Divided by 64 plus 36 is going to give me 100 times vector u. So this is really going to reduce to 3/10 vector u. And I want to find this, right? So y hat is 3/10 times vector u. Vector u had entries 8, 6. Let me go ahead. I'm going to bring the 1/10 in first. I'm going to leave the 3 out in front. Sort of break up my arithmetic that way on my vector. 8 divided by 10, I can reduce by 2. That's going to reduce to 4/5. 6 divided by 10, I can reduce that as well. Reduces to 3/5. So I brought in the 1/10, but now I got to bring in the 3. So then this is going to give me 3 times 4 is 12 over 5. 3 times 3 gives me 9 over 5. So I have my projection vector, y hat. But then z, I can now find z, that's y minus y hat. It's going to be vector y minus y hat. I can rewrite y hat. Then I have to rewrite vector y. Let's see what that was. That was 3, 1 was the vector. And in order to do this subtraction, I would say, hey, get that common denominator. What is 3 in terms of fifths? That's 15/5. And 1 is really 5/5. We'll do the subtraction. So vector z, 15/5 minus 12/5 gives me 3/5. And 5/5 minus 9/5 gives me negative 4/5. So now I have vector z, finally. And I think it's worth to give a shout out to the projection vector y hat. You know, even though neither of these are the answer to the question, they're very important milestones along the way. Now I want the distance from y to the line, so I have to find the length of this vector z. So I need the length or the magnitude of vector z, or the norm of vector z. And that's going to be given by the square root of, remember, we square these entries and we sum them. So 3/5 squared plus negative 4/5 squared. And that's going to give me square root of 3 times 3 is 9, over 5 times 5 is 25, plus negative 4 times negative 4 is 16 over 25. And if I add these together, 9 and 16 give me 25 over 25. And that's going to give me the square root of 1. Square root of 1 gives me 1. So we'll say the distance from y to the line through u and the origin is 1. Now, that was just by happenstance, right? Don't think we can always expect that the magnitude or the length of the norm of the vector z is going to be 1, but it is very, very cute that it worked out that way. So I'm happy with that. But that's how we'd go through and answer this question, right? A lot of work to get there, but the result was definitely very satisfying. We'll take a look at one last example, and then, hey, we're out of here. Let's determine which sets of vectors are orthonormal. If the set is only orthogonal, normalize the vectors to produce an orthonormal set. And I have two sets here. So I'm going to break the problem up like this, right down the middle. Now, what does it mean to have an orthonormal set? There's two parts here, and let me sort of talk about it. The ortho part means it must be orthogonal. You need orthogonal vectors. But then the normal part means they must also be unit vectors. So in order to have an orthonormal set, I need both of these things happening. I need an orthogonal set of vectors where the vectors themselves are unit vectors. Let me go here to this first set. Let me just call these vectors A and B, just so I have something to call them by. If I find their dot product, A dot B, 1/3 times -1/2 is going to give me -1/6. 1/3 times 0 gives me 0. 1/3 times 1/2 gives me +1/6. And hey, that's going to give me 0. So this is an orthogonal set of vectors. Now to determine if it's an orthonormal set, I want to check and see that both of the vectors are unit vectors. So I could just start by finding the length or the norm or the magnitude of the vectors. So here the length of vector A, well, that would be the square root of, I would want 1/3 squared plus 1/3 squared plus 1/3 squared. And that's going to give me the square root of, so here I'm going to get a lot of the same thing, right? 1/9 plus 1/9 plus 1/9. Or then that's going to give me the square root of 3/9. So we'll be able to say, okay, then the length of vector A, and if I do the quotient property of the radical 3 over radical 9 gives me radical 3. Well, let me actually reduce this first. That might give sort of a better result later on. So 3/9 gives me square root of 1/3. Then I can use the quotient property of the radical. Square root of 1 gives me 1 over square root of 3. So right away I can actually answer the question, right? Is this an orthonormal set? It's not. Because one of the vectors, at least one of them, so far that I know, is not a unit vector. It is an orthogonal set, since the dot product of the two vectors of the set give me 0. But it's not going to be an orthonormal set. So right away I can say this is not ortho. I'm going to run out of room, so let me write it down here. Not orthonormal. It is orthogonal, but it is not an orthonormal set. Now the follow-up says, if the set is only orthogonal, normalize the vectors to produce an orthonormal set. And we know how to do that. That means turn these into unit vectors. Now, I didn't check vector B, so I should do that. What is the magnitude of vector B? Or the length or the norm of vector B? That's going to be the square root of. We're going to have -1/2 squared plus 0 squared plus 1/2 squared. And what's that going to give us? Okay, let's find out. It's going to be the square root of -1/2 times -1/2 is +1/4, plus 0 plus 1/2 times 1/2 is 1/4. And that's going to give us the square root of 2/4. If I reduce this fraction, that's the square root of 1/2. So then the magnitude or the length or the norm of vector B, if I use my quotient property of the radical, square root of 1 is 1 over square root of 2. So neither of these, in fact, were unit vectors. They're both sort of messing up that orthonormal set. But I can build these into unit vectors. So maybe I'll call the vector u sub A for the unit vector on vector A. I would want to divide by the length of the vector, so 1 over radical 3 times that first vector. And that was just, was it 1/3, 1/3, 1/3? Now here what's nice about this, 1 over radical 3 is just radical 3 times the vector 1/3, 1/3, 1/3. So this is going to give me a vector. Let's bring that in. Gives me radical 3 over 3, radical 3 over 3, radical 3 over 3 for all entries. Let's find the unit vector in the direction of vector b. So I want to scale this by its length since it wasn't length 1. So that's 1 over radical 2 into vector b. And vector b had entries -1/2, 0, +1/2. Here 1 over radical 2 is just radical 2 times the vector. And if I bring that value in, I'm going to get negative radical 2 over 2, 0, and positive radical 2 over 2. And now these are now unit vectors. So now I've normalized the vectors. So my orthonormal set, let me do this in a different color so it's not just a bunch of yellow chalk. Let's do the pink. My orthonormal set is, it's going to be a set of 2 vectors. And the first vector, radical 3 over 3, radical 3 over 3, radical 3 over 3. Second vector is negative radical 2 over 2, 0, and positive radical 2 over 2. And let's take a look at, because there was another part to this question. But we've taken a look at this first half. You do this in a different color. So you have another set of vectors. Let me name these vectors something. Just name them v and w. Now I can start by finding the dot product. So v dotted with w. I can probably see by inspection, but let's show the work. It's going to be -0.6 times 0.8 plus 0.8 times 0.6. Now it's the same product, the same two numbers being multiplied. However, one product is positive, the other is negative. So that's going to give me 0. Right? So this is an orthogonal set. But what about whether or not these are unit vectors? What about the length of the vectors? Well, let's find the magnitude. So magnitude of vector v, or the length of the norm of it, is going to be the square root of -0.6 squared plus 0.8 squared. And then here, this is going to give me square root of -0.6 times -0.6 gives me 0.36, plus 0.8 times 0.8 gives me 0.64. If I add these together, it's going to give me the square root of 1, which gives me 1. So that is a unit vector. Now, you can imagine that when I go to find the length or the magnitude or the norm of vector w, it's not really going to be too different. Since I have 0.8 and 0.6 as the entries, it's the square root of 0.8 squared plus 0.6 squared, which gives me that familiar square root of 0.64 plus 0.36, which is going to give me square root of 1, which is 1. So that's a unit vector as well. So this set is already such that the vectors in the set are orthogonal and they're both unit vectors. So we can say this set is an orthonormal set. So this is an orthonormal set already, so I don't have to go through correcting it. Hey, I hope you enjoyed this lecture talking about not only vectors, but orthogonal projections, all sorts of fun stuff going on today. No matter where you are and what you're doing, I want to make sure that you'll always, promise me this, you'll always keep learning, keep dreaming, follow your heart. And hey, not going anywhere. We're going to be doing more math with cats. But until then, I will see you next time. See you later. Take care of yourself.